And we are moving on to chapter 29. So talking about, last chapter 28 was really about forces on moving charged particles. Now we're going to talk about magnetic fields due to currents. The fact is, anytime you have a moving charged particle, that creates its own magnetic field. Okay, and so we're going to take a look at that. There are different geometries of current and the types of fields that are produced. There will be a B field quiz. This is your last field quiz, right? We had the I quiz, we had the E field quiz, the E chart quiz. And so you can see the different types of geometries, things. If you have, first of all, a bar magnet, and then we have what's, a solenoid. Solenoid is, it's kind of like a coil, but it's lined up. A coil usually is just wires wrapped around. It's not anything where, it looks like a cylinder, like that solenoid thing. Just a ring is there. If you have a coil wrapped around a piece of iron or something like that, it'll set up a magnetic field in the iron. Or even just a wire by itself. That's the most basic one. A wire by itself produces a magnetic field around the wire according to the right-hand rule. Okay, and so let's put it this way. So magnetic fields are produced by moving charges. That's the basic idea here. And this is the Biot-Savart law to find the magnetic field due to any point. And simply put, dB, some small piece of the magnetic field, is due to some small piece of the current, and it's given by mu naught over 4 pi. Mu naught, by the way, is the magnetic equivalent of epsilon naught. Remember, epsilon naught was the permittivity of free space. Mu naught is called the permeability of free space, and that's 4 pi times 10 to the negative 7th Tesla's meters per amps, or Weber's per amp meters, right? There's so many different units that we've come up with by now. And so, so B is given by mu naught I over 4 pi, and then the integral of ds over r squared, and that is a cross product with r hat, the vector, the radius vector from the wire, whatever is carrying that current. And so the direction of a magnetic field is given by the right-hand rule. What you do is you stick your thumb in the direction of the current, and then these fingers, your other 4 fingers, are pointing in the direction of the magnetic field. And it actually produces a magnetic field in a circular kind of way, right? So the magnetic field arrows are pointing around the wire and in the direction of the magnetic field. Okay, so the magnetic field of various geometries from a thin, straight conductor of finite length would be mu naught I over 4 pi a times cosine theta 1 minus cosine theta 2. All right, that's it. But then if this thing is infinitely long, then you end up with 2, because the cosine of theta 1 is 0 if that thing is infinitely long, and theta 2 ends up being pi, right, or 180 degrees, and so you end up with 1 minus negative 1, so that's 2. So the geometry of a wire of infinite length is mu naught I over 2 pi a. That would be a good one to have memorized, because we're going to see it quite a bit. For a semi-infinite conductor, so you're at one end and then the conductor goes on forever in the other direction, that's mu naught I over 4 pi a. And that would be good to remember as well, because we're going to see situations like that. When would we use that? Well, if you've got a wire coming up and then taking a sharp turn, you want to know the magnetic field due to this piece here, if you're over here. And so, example 1, calculate the magnitude and direction of a B field due to a long, that's code for infinite, so watch out for those types of things. Straight wire carrying 5 amps to the north at a distance of 4 centimeters. Right, and all you're doing here is you're taking mu naught I over 2 pi a, the formula, and you're plugging in the numbers. Mu naught 4 pi times 10 to the negative 7th times 5 amps over 2 times pi times a, which is 0.04, and you should end up with an answer of 2.5 times 10 to the negative 5th Tesla. That's it. I'm not even going to write it down. It should, you're just plug and chug. Okay. Example 2, we're going to skip for the sake of time. You don't necessarily need it. But let's take a look at example 3. It says calculate the magnitude and direction of the B field at the point P as shown. And here the answer is 0. If you look at the formula for a finite line, you know, mu naught I over 4 pi a cosine theta 1 minus cosine theta 2. Theta 1 and theta 2, if you draw those, they're actually the same. They're both 0. And so you get cosine of theta 1 is 1 minus cosine theta 2, which is 1, so it ends up just being 0. So this is important. If you have a wire coming this way and a point here, the magnetic field here due to this wire is 0. The only time we get a magnetic field is when we are off of the length of that wire, that axis that wire is on. And so now C, so we're looking at this loop, right? This sort of circular loop from this thing. All right, so if we've got, let me do this way. If it looks like this, at this point, remember what we just said, magnetic field due to this wire is 0, the magnetic field due to this wire is 0, due to this wire is 0, and this one. So the only magnetic field we're getting is due to this arc. Okay, and that's given by mu naught I over 4 pi r times theta. Okay, where theta is in radians. If you have a current loop, so that thing goes all the way around, then theta ends up being 2 pi, and so it ends up as mu naught I over 2r. And if you have multiple loops, so if you have a wire and it's just wrapped around a bunch of times, again, not a solenoid where it looks like a cylinder, but just a circle wrapped around a bunch of times, a coil, then it ends up being mu naught I over 2 pi r times n, where n is the number of loops. You're just taking, you know, the formula for one loop and multiplying it by the number of loops. And then if you're some distance away from the axis of the circle, right, from the center of the circle along the axis, then that's given by mu naught I r squared over 2 r squared plus x squared to the 3/2 power. And then again, if you have n loops, then you just multiply that by the number of loops that you have.